Hi, welcome to section 7.2, which is on describing and analyzing data. We're going to talk about the measures of central tendency, which are the mean, median, and mode, and then we'll do some story problems, and then we'll end by talking about how to do a box and whiskers plot. So let's start with the measures of central tendency, and you may have seen these before. So we're going to talk about the mean first, which is also known as what we think of as the arithmetic average. So when somebody says, the average number of children in households in the United States is 2.4. Usually they're talking about the mean. It's also possible though that they're referring to the median or the mode. So when you hear the word average, when you're consuming, information, it's not always the mean, but I would say it's probably most often the mean. So the mean, the nice thing about the mean, and it could also be the downside too, but it considers all values in the set. So let's look at this example. So every single number in the list gets factored into the mean. And it means that, if there's unusually high or low values, it can throw this value off. So that's the downside of the mean. But all we have to do here is we're going to add up all of the values and divide by the number that we have. So if we add up all of these, which we can say, so I can just write the average is just the sum, so the total of the values divided by the number of values. Okay, so here if we add up all these numbers, we end up getting 43, and there's 6 of them, so we divide by 6, and we end up getting 7.16 repeating. So the average is about a little bit more than 7. And in this case, the numbers are, I would say, pretty close together. So, that's probably an accurate average. The nice thing about the median, which is the next one, is the median is resistant to those extreme values. And like I noted here, it can also be a weakness. So there's pluses and minuses to both. But the nice thing about the median, we're just finding the middle of the data set, the middle number, when it's in order. So that's really important, the in order part. If I just pick the middle number, that doesn't really tell me much if the numbers aren't in order, but if they are, it can tell me a good estimate for average. And then again, the nice thing about this, let's say there was a really big number at the end. So let's say this number was like 5,000. The median would still be 10 because that's the middle number, and it wouldn't be affected by the fact that there was this gigantic outlier on the end, as opposed to the mean, it would be affected by that. So with the median, we always just start on the outsides and just kind of work our way in until we get to the very center. Sometimes there is an exact center and sometimes there's not. So with this second list, let's look at this one. So we can start crossing off those outside values to try to get to the middle. And with this one, you can see that there's a tie. There isn't an exact middle. So what you do is I'm going to draw a line in the middle of those two numbers. We're going to add them, so 110 plus 112, and we're going to divide by 2. We really don't even need to do the math in this one because you could just ask yourself, well, what number is in between 110 and 112? And it's 111. But the nice thing about this is we do have a process in case, it was harder to compute just by head, in your head. So the median in this case is 111. So, one example that I like to give in class is just, sometimes when I grade test, actually most of the time when I grade test, I'll find the mean and median of the class scores. So that way it gives me some information. So I just want to go through an example with that data just to show you how you can use these together. So say, for example, I grade a set of tests and the class mean was 80%. But the median was 70. What does that tell you about the class? So the mean was 80 and the median is 70. So you could pause the video, think about that. Remember, with a median, if the median is 70, it means half scored above, half scored below. I'd be a little bummed. I'd be probably a lot bummed if the median was 70. It's lower than I usually like. But ask yourself, what does the 80% tell you about the class? Why is the mean 80? What about the class? What happened in those tests that made that mean go up? And the reason it's higher is that there's some students that scored really, really well in that high range. So we call those outliers, and they drove the average up. So in this case, I would look at this scenario and I would probably not pay as much attention to the 80. I would say, you know what, I'm going to pay more attention to the 70. That tells me that we really need to review some concepts. The 80 tells me that I have a couple of really bright students who scored really well, but generally the class didn't do that well. I'll give you another example. Let's say it was the other way around. So let's say my median was 85%. So that's pretty good. I'd be really happy with that. That means half the class scored above 85 and half the class scored below. So I'd be pretty happy with that. Let's say my mean, though, is 60%, which is not good. I wouldn't be happy with that. What does that tell me? So what about the class test scores brought that average down? In this case, I would say, well, I've got a handful of students who scored really, really low. I mean, maybe they got 5%, or maybe somebody didn't take it or missed it and got a 0, and it really brought that class average down. And so this tells me that I need to take those students who brought that average down and work with them, but overall, the class did really well. So it gives me, by having both of those together, it gives me a lot more information than if I just had one of them. And then the last measure of central tendency is the mode, and this is the most frequently occurring number, which you can think of as just the most typical. It's possible, I list out some options here in the table. So these are the possibilities. It's possible to have no mode. Check out this list of data. None of the values repeat, so there isn't a mode because they all occur once. In the second row, there's one mode, and it's 20. So we say the mode here is 20 because it occurs more than the other numbers. It's possible to have more than one mode. Now, in this case, I try to come up with an example that might challenge us a little bit more because we see these examples sometimes occur. So we've got the 2s repeat, the 5s repeat, and the 6 repeats. Now, just because a value repeats doesn't mean that it's considered a mode. So it's got to repeat the most. So in this case, I'm not going to consider the 5 a mode because it only occurs twice. I'm going to say 2 and 6, there's a tie there. They both occur 3 times. So I'm going to say the modes are 2 and 6. So it's possible to have more than one, but make sure that they occur the most. Okay, and then the next one, trimodal, it's possible to have 3 modes. So in this list, we've got the 0 repeats twice, the 4 repeats twice, the 7 repeats twice. So in this case, we would just list those out. So we would say the modes are 0, 4, and 7. And then lastly, it's totally possible to have more than 3, and there's, infinitely many possibilities. So in this case, it'd be 26, 27, 30, and 31. So 26, 27, 30, and then 41. Good. So let's do a couple of examples. So suppose the test scores for 14 students on their first math test of the semester are, and we've got a list of math scores. So this would be the perfect time to pause the video and find the mean, median, mode on your own. And then I'm going to go ahead and work through it. So the mean, we're going to add them all up and divide by 14. When I do that, I end up getting 77.357, which is about, we'll say 77%. I'm assuming these are percentages, but we'll just say the score is 77. The median, now this list is in order, so I can start by just crossing off the outside numbers and working my way to the middle. And I end up having a tie, so it's right in the middle of 78 and 82. So I'm going to say 78 plus 82 divided by 2, and you end up getting 80. So the median is a little bit higher. And you can see, look at these. So the mean is lower than the median, and you can see with the scores, there was some pretty, low scores, like 58 and 60 are fairly low, and that's what ended up bringing this average down. But overall, I think the class did fairly well. I mean, half the class scored above 80, which I think is great. And then for mode, look at values that repeat. Look and see if there's any values that repeat. And there are, it looks like 82 repeats, so we've got a mode of 82. So the measures of central tendency can be the same, but oftentimes they're different. In this case, they're pretty close together. So let's look at the second test. And we're going to do the same thing. So now we have 17 students, 3 more students added to the course. So we have more students than we did before. And so we're going to do the same thing as we did with the last example. So with the mean, and this would be a great time, pause the video and try this on your own. So we've got mean should be 1342 divided by 17 students. You end up getting 78.94. It keeps going. So I'll say about 79. The median, if we cross off the outside values, we end up getting a direct middle, an exact middle of 85. And then mode, it looks like we've got the 70s repeat, we've got some 85s repeat, and then the 90s repeat. Since the 90s repeat 3 times, so we're going to say that the mode is 90 for that one. So now, how do these tests compare? That's why we do these problems. So let me see if I can scroll up and you can see both at the same time. Let's compare those. So it looks like the mean was higher, the median was higher, and the mode was higher for the second test. And if you look at just the list of data, it's sometimes hard to tease that out. So I would say that, you know, the second test was better. So I'm going to say the second test had higher scores on average. And one thing to note is the student over here that got the 38, had that student not gotten that 38, if this outlier were higher, say it was even 65, these numbers would have been even higher. So I think that it's clear that the second test was better. And that's why there's such a difference between the mean and the median. That 38 is really bringing down the class average, but I definitely think the second test had a higher average. And then one thing I want to mention real quick with kids. So usually I remember teaching this for the first time in middle school in 6th grade, and I remember the students sort of struggling, fumbling with the numbers, especially larger data sets, and I ended up having them use centimeter paper. So you can print these off online for free, but centimeter paper is basically just like grid paper, but the boxes are each a centimeter by a centimeter, so it's a little bigger. And what I do is I have them cut out a row of the paper or a column, and they write one number in each box. So, you know, they write a 38 and a 65, and this really helps them organize their numbers well. You know, it's super simple, but I'm telling you, it was a game changer. And then what you do to find the median is you have them just fold the list in half, and in this case it would literally fold directly on the 85, which would tell you that's the median. And then if there was a tie like above, the fold would end up occurring between the two numbers, and then you would know you had to add them and divide by 2. And you can even have students use scissors and cut the list either in half or through that number, and it makes for a really clear demonstration. So let's put this, let's put these measures of central tendency to test here, and we'll do some story problems. So take a look at example 2, and this would be a good time to pause and think about this on your own first. So which measure of central tendency, mean, median, or mode, is best for describing the following instances? So the typical size of hats sold in a store. So if you think about hats, there's different types of ways hats can be sold. I mean, there's sizes in inches and sizes in centimeters, and then you have small, medium, and large. Let's just make it simple, and let's say that the hat store has extra small, small, medium, large, and extra large. So if you were a store owner and you had a list of the typical sizes of hats, you know, it would be a list of, you know, I've got maybe 4 extra smalls, and maybe I sold 15 smalls today, and maybe I sold 25 mediums, and maybe I sold 30 larges, and maybe I sold 15 extra larges. What measure of central tendency? The mean. So should I average all of these numbers? The mode, which one occurs the most? Or the median, if I put them in order from least to greatest, which one is in the middle? To me, and I think these are, you can argue with these, I mean, there's not one right answer, but I think the mode makes more sense because that's the value that occurs the most. So I'd want to know that large is sold the most, that would help me as a store owner to make sure that I buy more larges, and I'd want to know that exact value. So I'd want to know, yeah, there were 30 of those, and then I'd probably want to know the other ones too, just in order, or the ones that came below large, so that I could order those appropriately too. So the next one, the typical heights of players on a basketball team. So think about, if you have a basketball team, and I guess it just depends what kind. I mean, if you have a kindergarten, first grade basketball team versus a pro basketball team, you're going to have different numbers. But let's just assume here that we're looking at pro basketball. So like the NBA. If you think about those players, they're mainly tall. Sure, there's some outliers, but they're mostly tall. In this case, I would say probably the mean would be helpful. There aren't really many outliers that are going to throw that off too much. I wouldn't want to do the mode, because even though they're probably all around the same height, you might not have any players that are the exact same height, so the mode might not be helpful. I would say the median would be okay too. So if you think median, I could see how you could use the median as well. I think the mean would probably be the most helpful. And then the third one, the typical age of 7 people in a family, if 6 of them are under 40 and 1 is 96 years old. This is one, since there's this extreme outlier here, I would definitely say the median. And I would say the median, so the outlier doesn't throw off the data or throw off the average. So if you average all of their ages and then threw in that 96, you get an average that is over 40, which doesn't tell you much about the main ages of the main family members. So let's look at example 3. So when 100 students took a test, the average score was 77.1. 2 more students took the test. The sum of their scores was 125. What is the new average? So when I read a story problem, I really want to look at the question first. So what is the new average, to know what I'm aiming for? And then I'm going to start just kind of slowly going through the problem again and writing down what I know. So we've got 100 students took the test. So 100 students. And the average, we're going to assume this is mean, of those 100 students is 77.1. Now before I even go on to the 2 more students part, I'm going to kind of put this together and see if I can do something with those numbers. I know that the average, or mean, is the sum of all the scores divided by the number of students. And since I know 2 of those, so I know the mean, 77.1, and I know there's 100 students, I can actually solve for the sum. So just knowing that I've got 2 out of the 3 pieces of information there makes me want to solve that, just because that would give me more information. So if I do that, I end up just multiplying both sides by 100 to solve for x. So if I come over here, I end up getting that times 100 just moves this decimal 2 spots over. So I don't even need a calculator. So 7710 equals x. So that's the sum. So that's the sum of the 100 test scores. Now, the awesome thing is, now that I've got that sum, is now I can go to this next part. So 2 more students took the test. So now I have a total number of students of 102. And then, because I did have 100 and now 2 more took the test, the sum of their scores was 125. What is the new average? Well, if I want the average of the entire class, then I'm going to take the original sum, 7710, plus the new sum, 125, that's for my 2 students, and divide by the total number of students. So just to back up for a minute, I'm just going to delete this so I've got some more room here. On the top, that's my sum. On the bottom is the number of students. So this is, I'm just doing the average formula. So sum divided by the number of students. And so if I do that, I end up getting 7835 divided by 102, and I end up getting about 76.81% there. And so it's important. One of the mistakes I see students make a lot of times when we do this in class is that they'll look at the 125 and say, oh, if 2 students took it and got 125, well, we'll just divide that by 2. What is the problem with that? So it gives you an approximate average for those 2 students, but it doesn't give you the class average. And so that's why I ended up adding it to the previous and that gives me the whole class average, which is what the question is asking. All right, so we've got 2 more. So example 4. So we've got an ice cream shop. Owner hires a clerk and informs him that the mean weight of scoops of ice cream should be 46 grams. The clerk weighs out 6 ice cream scoops with the following weights. How many grams of ice cream should be added to the smallest of these scoops to obtain an average weight of 46 grams for the 6 scoops? So here's the thing. If you're reading this and you're overwhelmed and not knowing where to start, I would pause the video and I would read it on your own and see if you can draw a picture. So I want you to think about, we've got these 6 ice creams, 4, 5, 6, and they each have weights. So we've got 38, 40, 43, 44, 46, and 41, okay? And we want an average of 46. So we want to know how much ice cream should be added to the smallest. How much more do we have to add to this guy, because that's the smallest, in order for this average to be 46? So there are several ways to do this. You can do it algebraically. You can do it by guess and check. So what I would do is just start by adding these up, okay, and dividing by 6. What do you get when you divide those or add those up and divide by 6? If you do that, you end up getting 42, an average of 42. Well, that's too low. So we want an average of 46. So we know we have to add more. So this is one thing you could do. You could take this sum and you could start adding to it. So if the sum, actually let me write out this, the sum is 252 when we add those up. You could start by adding, just experimenting. Take your calculator, do 254 divided by 6, 255 divided by 6, 260 divided by 6. Keep adding and see what you need in order to get the 46 as an average. So that would be one way to do it. The other way you could do it is you could do it algebraically. You could say, well, 252 plus what divided by 6 is equal to 46. And then we're going to solve it by multiplying both sides. Use a different color. Multiplying both sides by 6 because that goes away. And then we can write down 252 plus x equals 46 times 6. So 46 times 6 is 276. Okay, so that's the total that we end up needing for that. And then I subtract 252 from both sides, and then we end up getting 4 and 24. And so 24 is what we would need to add to our original sum in order to get an average of 46. And sure, the problem says add it to the small scoop, but really it doesn't matter where you're adding it, you're just adding it to that sum. So the answer here is 24. Okay, so let's go on to number 5. Okay, so for number 5, in Lee Middle School, the ratio of the number of 5th graders to the number of 6th graders is 4 to 3. So I'm just going to write out 5th to 6th is 4 to 3. And you can also write it like this. There are 18 more 5th graders, so 18 more 5th graders than 6th graders. And then if the ratio of the number of 6th graders to 7th graders, so I'm going to write over here, 6th to 7th is 2 to 3, what is the mean number of students in the 3 grades? Okay, so, well, if we want, let's first underline the question. So what is the mean number of students in the 3 grades? If we want the mean number of students, then we need to know the total number of students in each grade. So in order to do that, let's start just on the left here and let's look at the 5th and 6th graders. So if I know the ratio is 4 to 3, You could do this by guess and check and drawing a picture. You could draw a picture where maybe fifth graders are X's, and you say, okay, there's 4 fifth graders for every 3 sixth graders. We'll say sixth grade's Y. Right now we have 7 students and there's 1 more fifth grader. You could keep doing that until you end up with 18 more fifth graders and see how many you end up with. So that would be a good visual way to do this. Algebraically, you could come over here and just use this proportion. If we know if there's a ratio of 4 to 3, and I'm writing fifth on the top, I'm labeling this sixth on the bottom. If there's 18 more fifth graders, what I can do is I can say, well, I'm going to call sixth graders X. And if there's 15 or 18 more fifth graders than sixth graders, then all I have to do here is write 18 plus X. And then I can go ahead and I can solve the proportion. So 3 times 18 plus X equals 4 times X. And then I could go ahead and multiply that 3 in. So I get 3 times 18 is 54 plus 3X equals 4X. Subtract 3X from both sides. And I end up getting, I shouldn't have actually crossed that out. So 4X minus 3X. So I get 54 equals 4 minus 3 is 1X. So it means, again, X is sixth graders. So there are 54 sixth graders. Okay, and then I know that there are 18 more fifth graders. So all I have to do here is I have to take 54 plus 18, and I get 72 fifth graders. So I know that there are 72 fifth graders and 54 sixth graders. And then just to double check, you can divide and make sure that ratio holds true. So do 72 divided by 54, and you'll get the same thing you get when you do 4 divided by 3. So now I can go ahead and I can go over here to the 6th and 7th grade ratio. So I'm going to say, so I'm just going to move this over. Whoops, and there we go. Okay, so 6th, 7th, we get a ratio of 2 to 3. I know how many sixth graders, oh, my eraser is acting crazy. So 6th, 7th, so we said 2 to 3, and I know there are 54 sixth graders now. So I can just say, okay, well, there's 54. I can put that on the top with 6th grade, and then I can say X down here because I can solve for the 7th graders. So I'm just going to do 2 times X equals 3 times 54. So I'm going to come over here, and I get 162. So I get 2X equals 162. And then I divide that by 2, and I end up getting 81. So, and that's 81 is my X, and that's 7th grade. So then I've got 81 7th graders. Okay. And then it asks, what is the mean? So then you're going to find the mean by adding those up, and you're dividing by 3. So you're going to take 54 plus 72 plus 81, and you're going to add that all up. So I should have done that ahead of time. I'm just going to do it on my calculator real quick. So 54 plus 72 plus 81 equals 207. And then you're going to take that and you're going to divide it by 3, and we get an average of 69. And always ask yourself, does that make sense? Well, 69, if you look at those numbers, that seems reasonable. It seems like sort of a good middle estimate there. So that concludes the examples that have to do with average, and those are definitely not easy. So those are examples where you might want to try. I hope you already tried during the video on your own, but if you didn't and you just listened to me explain it, I would definitely go back and try to do those on your own, and that way you have the video to rely on if you need some help. So the next part we're going to jump into, the last part, is the box and whiskers plot. So the box and whiskers plot is a type of plot that you don't see very often in real life. The place that I've seen it the most is probably when you're reading students' standardized test results. A lot of times their results will come in what's called a box and whiskers plot, and you may have seen this before. And usually what it looks like is there's a box with a line, vertical line somewhere in the box. Maybe it's off to the side, it could be in the direct center, and then there's these two horizontal lines on either end, and we call those the whiskers. And basically the box and whiskers plot highlights we call it the 5-number summary, and it highlights 5 important numbers. The first one is the lowest value. So I'm just going to put an L here. It's the smallest number in the list. Okay. And then it highlights the highest value up here. I'm going to put an H there. And then it highlights the lower quartile, which we call Q1, the median, which is Q2, and the median is always this line that's inside the box there, that vertical line. And then Q3, which is this number, it's the end of the box. So the Q3 is your upper quartile or your third quartile. And I'm going to show you how to find all of these quartiles. Let me just give you a really simple example before we jump into the bigger examples. Let's say you had a list of numbers like 3, 5, 7, 9, and 11. So your lowest number would be 3, your highest would be 11, and then I would find the median, which is Q2, and that's number in the very middle, which would be 7. So median, I'm going to write median, which is also Q2. And then your Q1 is the middle of the lower half. So you ignore the median and you look at the lower half and you figure out, well, where is the middle there? Well, my lower half is 3 and 5. So the middle is going to be between those two numbers. So 4 is in between 3 and 5. So that's going to be your Q1. And then the middle of the upper half, which is 9 and 11, that would be 10. And that's going to be your Q3. So your 5-number summary is going to be 3, 4, 7, 10, and 11, and then we plot those on a number line and make this box with them. So we can do a lot with the box and whiskers plot. We can find, it's called the interquartile range. We're going to come back to that. We can find outliers very nicely with it. We're going to come back to that. We're going to do an example first, and then we'll come back and do those after we're done with an example. So I would definitely advise, if you're doing this with students, probably in either 5th or 6th grade, have them do this on centimeter paper, so that way they can write every number, like I said before, on centimeter paper, and it makes for finding the median a little bit easier. So let me go ahead and do, these are the test 1 and test 2 that we've already done before. So for test 1, we found that the median was 80, and I'm just going to go ahead and do that real quick again. So I'm going to start eliminating the numbers from the outside and get to the middle. And if I do that, I end up with a middle right here. And remember, if there's a tie, we can just do 78 plus 82 divided by 2. Or we could think to ourselves, what number is in the middle of 78 and 82 on a number line? And it would be 80. So 80 is our median. I put an M there, but that's also Q2. So 80 is Q2. Now the most important part with box and whiskers plots is after you identify the median, you have to not include it when you're finding the middle of the lower and upper half. So you're not going to include that 80, and what you are going to look at is you're just going to look at 58 to 78. And then you're going to look at 82 to 94, and you're not going to include that 80. So then we look on the left side, the lower half of the data, and then we eliminate those one at a time, and we try to find a direct center. Now in this case, 70, we didn't have to average. 70 is our middle there. So we call this Q1. So I'm going to write down 70, and then I'm going to do the same thing with my upper half, and we end up getting 86. And then our lowest value is 58. And our highest value is 94. And so that's your 5-number summary. Now with kids, this takes a long time. Like writing it on centimeter paper will help because it'll help them organize their numbers, but trying to remember that you don't include the median, that's an important one, and it's just an easy one to sort of forget about, and then it messes up your data. So just pay close attention to that. So this would be a great place to pause the video and you know, try to do test 2 on your own. And I'm going to go ahead and work that out. So 38 is my lowest value here, 94 is my highest, and then I'm going to go and I'm going to find the very center of test 2, and if you do, you end up finding that this 85 right here is the very middle. So I've got my left half and my right half, and I'm going to write down 85 for my median, which is Q2, and Q1 is going to be the middle of the left half. So I'm going to go ahead and find the middle of those, and it looks like directly in between the two 70s. You don't even have to add those up and divide by 2. The middle of 70 is 70, so that's Q1. And then I'm going to go ahead and find the middle here, and that's going to be 90. 90 plus 90 divided by 2 is 90. So you can still go through the process if you need to, but you don't have to, since they're the same number. So we've got the 5-number summary for both. So then at this point, if you want to graph a box and whiskers plot, whoops, I just turned off my power. Hold on just one second. If you want to graph a box and whiskers plot, what you're going to do is you need a number line. So this line down here, we're going to use this as a number line. And since my data goes from, it looks like 38 to 94, I'm going to start at 20 and work up in tens. 30, 40, 50, 60, 70, 80, 90, 100. And I'll put a line in the middle for the 5s. And then what you're going to do, I'm going to go ahead and do test 1 first. So I'm going to come up here, test 1, and I'm going to put dots next to each one of those numbers, above each one of those numbers. So I'm going to put a dot above 58, and then above 70. So I'm looking at these 5-number summaries right here. And then 80, and then 86, and then 94. And then you're going to take the outer dots, we're going to make a whisker with those, and then the inner ones are going to get a box, and then we're going to draw a vertical line through the middle, and there's your box and whiskers plot. And so this is test 1. Okay, and then for the next one, I'll go ahead and use a different color. So for test 2, I'll use red, and I'm going to go ahead and do the same. So I'm going to put a dot, I'm looking at test 2 now, so a dot above 38, and I'm going to go way up here. Makes it a little bit harder to be exact, but that's okay. I'm going to go above 70, and then I'm going to go above 85, and then above 90, and then I'm going to go to 94. And so I'm going to make a whisker on the outer parts, and then I'm going to make a box in the middle, and then my vertical line. And so this is test 2. And if you want, you can label it. So this is my lowest value, and this is my Q1, my Q2, my median, my Q3. So a couple things I want to talk about with box and whiskers plots. So how do we interpret what they mean? Well, take a look at the first one. You've got, or test 2, you've got a really big whisker on the left-hand side. What does that represent? So what does that mean? If you have a really big whisker, what does that mean in terms of the data? If you look at the data, we divided the data into 4 sections. So that's why they're called quartiles, because when you have 3 quartiles, you divide it into 1, 2, 3, 4 sections. And so this lower section here, which is right here, do we have any more data values in that section? Well, no, they each have, it looks like, 4 in them. So why is this whisker longer? It doesn't have more scores in that area. What it means is that there's a greater range. So whenever you have larger sections of your box and whiskers plot, that represents a larger range in data. So that's really important. So bigger sections means a bigger range in the data. So test 2 scores, I would say looking at the box and whiskers plots, there was a greater range in values with test 2 compared to test 1, specifically with the students that scored in the lower quartile, in the lower 25%. And that's another thing that's worth talking about here. I'm just going to use a different color. If we're dividing the data into 4 sections, then 25% of the data values are going to be in each piece. So 25% in each piece. So if there's a smaller section, So maybe like this section right here with test 2, it just means that those students, those scores in that section, the scores were very similar. And if we look at that section up here, they are. We've got 85, 86, 87, 90, and they're a little bit tighter together than this first section where we've got everywhere between 38 and 70. So a couple other things we can do. We can find what's called the interquartile range. So the interquartile range, and we have that in our notes above, so you can just scroll up above. The interquartile range, it's super simple to compute. It's just Q3 minus Q1, so it's a simple subtraction. So we can find the IQR for both of them. So for test, and actually I'll write it right next to the box and whiskers plot. So IQR for test 2, we're going to take Q3 minus Q1. So Q3 is 90. Minus 70, so the interquartile range for test 2 is 20. That tells you how big the box is. So that's test 2. Let's do it again. So the interquartile range for test 1, we're going to take Q3, I'm going to scroll up so I can see the exact values. So we got 86, which is Q3, minus 70. Equals 16. So it's a little bit smaller of a range. And if you look, the box for test 2 is smaller than the box. It's a smaller range than the box in test 2. The box for test 1 is smaller than the box for test 2. So that's how you compute the interquartile range. And then that's helpful because it can help you find what are called outliers. So I'm just going to scroll up and I'm going to find the outliers for both of those. So if we want to find, and I'm just going to do, actually, you know what, I'm just going to do it for test 2. So let's find outliers for test 2, or we're going to look for outliers. We don't know if we're necessarily going to find them. So we're going to do what's called we're going to find the lower bound and the upper bound. So the lower bound equation, it's above in your notes, is Q1 minus 1.5 times the interquartile range. So we're going to take Q1 for test 2, which is 70, minus 1.5 times the interquartile range, which we just calculated, is 20. And then we're going to work that out, and we end up getting 40 for a lower bound. Then we're going to find our upper bound, and I'll explain what these mean in a minute. And the formula for upper bound, and it's above in your notes, is Q3 plus 1.5 times interquartile range. Q3 for test 2 is 90 plus 1.5 times 20. And if you work that all out, you end up getting 120. So what this means is that there's a range. If there's any values that are less than 40 or greater than 120, then those are considered outliers. So the lower bound and upper bound tell you anything in that range is considered normal. Anything outside of that range is considered an outlier. So if we scroll up, let's look and see, are there any values that are outside of 40 to 120? And there are. We had a test score of 38. So we say therefore, which is just this triangle made with dots, stands for therefore. So therefore 38 is an outlier. And that, and we might have been able to tell that just looking. I mean, we could have guessed and you know, seen that 38 was much farther below the other values, but this gives us an exact way to determine that. And you know what? I actually said this was the last section, and I apologize. I totally didn't look and see. We've also got to talk about measures of variability. So this is actually, I promise this time, this is the last section of 7.2. So we're going to talk about measures of variability, which are range, mean deviation, and standard deviation. And these are important because sometimes the mean, median, and mode, they don't tell the whole story. So here are some examples. So check out these two classes. Let's say, for instance, and I know this is kind of a weird example, you don't often get test scores like this, but let's say you have 5 people in your class, and this is how they scored on the first test, and this is how they scored on the second. If you take the mean, median, and mode of those, you get the exact same thing. Yet look at the scores they're starkly different. So this first class tells me, hey, I've got some students that I really need to work with, and then some students who are doing fine. The second class, or it tells me that I've got to work with all of my students because they're all doing poorly. So totally different story. So the range is a really easy one to do, and that just tells us it's basically the high value minus the low. So just like we talked about at range in Box and Whiskers Plot, how far does the data span? So we can calculate the range for the first set. We're just going to do 100 minus 0, and we end up getting 100. So that's class 1. So there's a really big range there. Class 2, if we take the highest, which is 52, and we subtract 48, we end up getting a range of 4. So right there, that was a really simple way just to see or put a number to describe that the range is much greater in class 1 than it is in class 2. The other two that we're going to talk about, I'm sure you've heard of standard deviation before. We'll definitely get to that. We're going to start with mean deviation. So mean deviation is a little bit easier to calculate. So when we're working with younger students, like in middle school, this is definitely in 6th, 7th, and 8th. This is usually something that most teachers cover because it's a little bit easier to calculate than standard deviation, and it gives us another measure to approximate how far the data is going to vary from the mean. So below are the steps for mean deviation, 1, 2, 3, 4, and I'm going to go ahead and walk you through that with this first example. So step 1 is to find the mean. Oh, I keep turning the power off. Sorry about that. I don't know why the power button on my screen is right near my hand where I need to write. So the first step is to find the mean. I already did that for you. So we have this class set of data. The mean is 50. Then step 2 is to find the differences between each data value and the mean. So here are the data values. The first one is 0. So I'm going to take 0 minus the mean, 50. I get negative 50. Second one, 10 minus 50. I get negative 40. 50 minus 50. So I'm taking the data value here and I'm subtracting the mean. 90 minus 50 is 40, and then 100 minus 50 is 50. And then the next thing I do, step 3, is I find the positive difference. So that's really important here because some of these values are negative. Find the positive distance and then determine the mean of all of those positive differences. So to find the mean deviation, so the mean deviation, I'm going to take the positive differences, meaning if I wrote negative 50, I'm going to write positive 50 plus positive 40 plus 0 plus 40 plus 50. If they're already positive, you just leave them positive. So I'm taking, these are all the positive differences that I got from this column. And you're going to find the mean. So that means you're going to add them all up and you're going to divide by the total. And there's 1, 2, 3, 4, 5 values. So you add them up and you divide by 5. When I add them up, I get 180 divided by 5. I end up getting a mean deviation of 36. You could almost think of this as like the average distance that any of these values are from the average. So you can see that the differences, you know, they vary anywhere from 0 to 50. So we're averaging that out at about 36. The next part, standard deviation, it's a little bit more lengthy. And standard deviation is just a way of figuring out about how far a value differs from the average. It helps us compare a data value to the norm. So one example of this might be like standardized test score. So say, you know, I had a student years back who had a son and he was taking the ACT, and she told me that she was disappointed. And I said, well, what did he get? And she said, well, he got a 31 on the math. I think it was 31. It was either 31 or 32. And I was like, you're disappointed? Wow, that's a great score. And she said, yeah, well, the highest score is 36. I really wanted him to get a 36. So I actually pulled up the chart and the standard deviations for the ACT, and we found out that he was more than 2 standard deviations away from average. And I told her, I said, he is in like, you know, he is outside of 95% of the population. So he did better than 95% of the population. And just looking at that from that perspective, she was able to see, oh yeah, I guess he did do really well. So it helps us kind of compare a value to average. So the way that we find the standard deviation is we first find the mean, which I already did, it was 50. Then we subtract, so it's actually the same step that we just did, this second row where we subtract to find data value minus the mean. We're going to do that. Then we're going to square the number. So I'm just going to take the value here and I'm going to square it. Really important that you use parentheses when you do this in the calculator, because if you don't put parentheses here, you're going to get a negative 2500, and you shouldn't, because negative 50 times negative 50 is a positive 2500. If you do this in your calculator is going to use the order of operations and square it first, then make it negative. We want our calculator to do this, and that's why we have to put parentheses. So we should end up getting positive answers for all of these. So we should get 1600, 0, 1600, 2500. Another thing you could do is just forget the negative altogether and just do 50 squared in your calculator, and then you don't have to worry about parentheses at all. So then the next step, so we just did step 3, square the numbers from step 2. Step 4 is to find the sum, so we add them all up, get 8200. Then the next step is you divide by, so you divide the sum by n, and this is actually a typo, and I should fix this by the time you see the notes. It should be divide the sum by n minus 1, where n is the number of data values. So if n is 5 in this case, we're going to do n minus 1, or 5 minus 1, and we're going to divide this by 4. So if we divide that by 4, we end up getting 2050. And then it feels like we should be done because it's a really long problem, but we're not. We've got one more step. We're going to take the square root. So we take the square root of 2050, and we end up getting about 45.3. So this is the standard deviation, okay, for that problem. And basically, what this means is that if you were to draw a picture, let me come up here and see if I have a room for a picture. If you were to draw, call it the normal bell-shaped curve, and you were to put the middle as 50, which is the median. If we have a standard deviation of 45, it means if you're one standard deviation above the mean, which we could say plus 1, you're going to be, we do 50 plus 45, or 95.3. If you were one standard deviation below average, it'd be 50 minus 45.3, or 4.7. So it means that if you're anywhere between 4.7 and 95.3, you're one standard deviation away from the mean, which is still, you can see that's the bulk of the curve. You're still in that average range, and you can keep going and find 2 standard deviations and 3 standard deviations on either side if you want. We don't get that far in this class, but it's just I just want to give you some perspective if you're wondering what this means and how you might use it. So there is another example here, class 2. This would be a great one to pause the video and try this on your own. I'm going to go through this one a little bit more quickly just so that you can see the answers. So the mean for this one is also 50. I'm going to take the data value minus the mean, 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 and data value minus the mean. Okay, I'm going to find the mean deviation. I'm just going to say MD, and I'm going to take the positive differences, so these numbers, but I'm just going to write the positives of all of them, and I'm going to add them up, and I'm going to divide by 5. And then I get 6 divided by 5, or 1.2. That's my mean deviation. Okay, so then I stop there for the mean deviation. And then for the standard deviation, I keep going, and I square that number. Okay, I square all those, and then I add those up. I get 10, and then I divide by n minus 1, which is 4, because n is 5, so 5 minus 1 is 4. That's n minus 1. So I divide 10 divided by 4, and I get 2.5. And then I take the square root of 2.5, and I get approximately 1.58. And just look, whatever the book says in terms of rounding directions, that's what you will use. So you get approximately 1.8 for the standard deviation. And then last but not least, I would say in general, at least if we don't know much about the data and what type of data it is, you can assume that at least 75 of the measurements in any set of data will lie within 2 standard deviations of the mean. So if you have your mean value, to get 1 standard deviation above average, so this is 1 standard deviation, and then we'll say 2 standard deviations, and I'm going to go on the other side. So 1 standard deviation, this is below, and let me write above here, and above. And then you're going to go 2 standard deviations below. So what you can do, I'm going to use this very last example to give you an idea of how this would work. So let's say that our average, well, in this case, it's 50. Let's just round, well, I'll leave it as 1.58. That's fine. So to get, what we can do is we can draw this little chart, and then for 1 standard deviation above, all I have to do is add the standard deviation. So 1.58. So it's going to be 50 plus 1.58, which is 51.58. And so you're going to write 51.58. That's the value that's 1 standard deviation above. Then you can add the standard deviation again. And I'm adding 1.58 because that's what I calculated as the standard deviation. If I add it again, I get 53.16. Then I'm going to go the opposite way. So then I'm going to subtract 1.58. So I'm going to do 50 minus 1.58, and I get 48.42. And then I subtract 1.58 again to find 2 standard deviations below average. And so what this means is the 75% rule is it means that 75% of the data is going to be between 46.84, which is this number right here, 2 standard deviations below. It's going to be between 46.84 and 53.16. That's what that tells you. So you can use the mean and then the standard deviation that you calculate in the problem to figure out what that range is. And it tells you, so in this case for my class, it means that most of the students are going to be between those 2 scores. Hopefully not. Hopefully they're doing a lot better. But okay, so that is it for 7.2. As always, let me know if you have any questions.